All right, well, so we're going to continue chapter 11, talking about experiments. So in the last video, we kind of introduced the difference between an experiment and an observational study. So an observational study is basically where you set up kind of a survey. You throw out questions or choices and you let people choose whatever they're going to choose, and basically you kind of observe as things happen, and you're not manipulating anything, you're not changing anything, you're not affecting anything in any way other than putting options out for people to choose, and then you observe the results. With an experiment, on the other hand, you are the one assigning the choices to the people in the experiment or the objects in the experiment. You assign people to play an instrument, you assign people this, you assign people that. And so we talked about how the different choices are called factors. And so, or the different things that you assign, I should say. And then each factors would go with the variables that we talked about in chapter 1, categorical or quantitative variables, typically categorical in these types of experiments. And then however many different choices each factor has, those are called the levels. So the example we used last time, playing an instrument or not, that would be those would be the levels of the factor. And then the combination of the different levels is called the treatments. So what we're going to talk about now is going a little bit farther into the experiments. And the first topic is called statistical significance. And this is basically what we're trying to accomplish, or to see if we can do with an experiment. Statistical significance. So let's just bullet points on this example. So new running shoes guaranteed to make you faster. So someone decides to try these out and decreases her standard time of 55 seconds in the 400-meter run by 2 seconds. So is this due to the new shoes, or is this random variation? So in other words, maybe she's having a good day, or had a good stretch of however many times she ran this. If the standard run deviation of her runs is 1 second, then the new shoes are 2 standard deviations faster. So in other words, standard deviation would be 0.5 seconds. So 1 second would be 2 away. It would be even better if the average of 10 runs is 2 standard deviations faster. So in other words, if she does the run once and it's 2 seconds faster, that could just be, like I said, due to, it's a good day, feeling good, you run a little bit faster, that kind of thing. But if you're doing it 10 times in a row, then now maybe we're 2 standard deviations faster. Maybe that is something that we could say is due to the only change, presumably, that she made, which would be the shoes. And so a difference is statistically significant if we do not believe that it's likely to have occurred only by chance. So a difference of 2 seconds, maybe that is just kind of by random chance. I just noticed I misspoke here. Standard deviation of runs is 1 second. So 2 seconds would be 2 standard deviations. I misspoke there. I misread that. In any case, statistically significant means that you would not attribute this difference to random chance. So we talked about in chapter 10 how you're going to have differences in your data from sample to sample. Minor differences are normal. This is talking about where it's a greater difference due to something that you've changed. That would be statistically significant. So possible box plots. We can see, looking at these two box plots, that the box in this one is basically entirely above the box on the other one. Maybe Q1 here is about equal to Q3. But essentially the entire box here is entirely above this box. And the median in particular is completely above this box. So statistically significant, since the medians of each other are outside the typical values. And I guess with the running, we'd probably want the lower box would be better. But either way, the median is not in the box of the other one. Whereas this one, not statistically significant, this median would be in this box, this median is in this box. So those are not, we would not consider those statistically significant. So you need to be able to compare the data, because obviously, in a short race like this, 2 seconds is a big deal. If you're running a marathon where it's 26.2 miles, 2 seconds is not going to be that big of a difference. So statistically significant is obviously relative to what your data values are, but we can always look at a box plot, because the box plots typically are a good indicator of where the typical range of values are, and if we have a new data set, is it statistically different? And that's a good visual way to make that observation. All right, so next we have blinding, and probably most of us are familiar with some sort of blinding. They used to, I don't know if they still do, but they used to have taste test commercials where they'd have Pepsi and Coke, and the labels would be covered so you couldn't tell, and then they'd have people taste and then say which one they prefer. And so that's a very classic case of blinding, where the participants don't know which, are they drinking Pepsi or are they drinking Coke? And so that way they're not influenced by looking at the label. So that would be single blinding. Participants do not know whether they are in the control group or the treatment group, or which soda can they're drinking. If the person handing out the cups hands out her favorite soda, she may bias the results. Double blinding means neither the participant nor the person handing out the soda knows the label. And double blinding, a lot of times, that you could do that in medical trials where the participant does not know which medical treatment they're getting, and then the person evaluating to see, kind of measure the improvement of whatever condition they're looking at. If the person doing the evaluating does not know, then that would be double blinding. So, and going along with that, we have placebos. Placebos are fake treatments that look like the treatment being tested. So again, in medical trials, if you're giving some kind of medicine, a lot of times you give the actual medicine to half the people, and then something that looks like medicine, but it's not really anything, to the other half. And then you see if there's any kind of difference. And we've all heard of the placebo effect, where people think they're getting medicine, and then they somehow get better. So, all right. So another example here with nail polish. So comparing nail polish on real hands. So you could define each hand to be a block, randomly assign half the right hand fingers red and the other half blue. So we talked about blocks last time. So blocks are ways to divide your sample into groups, and the groups are divided in such a way that you think those groups will affect the results, but you don't really want to randomize by that, so you divide up by blocks. So you do the same for the left hand. Randomization occurs only within the blocks. This design is a randomized block design because we have the blocks. And the hands are the blocks. So blocking versus stratifying. So these are kind of similar ideas. We talked about stratifying in the last chapter. Stratifying is where you divide the population into groups called strata, and they're not random groups. They are such as male, female, or dividing the college by major, things like that. So blocking for experiments is the same idea as stratifying for sampling. Both methods group together subjects that are similar, so majors, like we talked about, randomize within those groups as a way to remove unwanted variation. This is just kind of something to point out, not really a testing kind of thing, but we don't say stratify an experiment and we don't say block an example. They're I guess, analogous terms for different things. So you stratify a sample, you block an experiment. We use blocks to reduce variability so we can see the effects of the factors, not interested in studying the effects of the blocks. So that's, again, you're not randomly assigning these things that you're blocking. You are dividing up by the blocks so that you know that the factor is the thing that is causing the change, or if the block is causing the change, you can at least see that, but that's not what you're studying. So last example, animated teaching versus subdued teaching. So we have a professor taught the same course in the fall and the spring and kept everything the same except for the style. So in the fall, he taught in a subdued manner. In the spring, more enthusiasm, animated gestures, that kind of thing. And the results, so how much did you learn on a scale of 1 to 5? In the fall, average was 2.93 versus the spring 4.05. So is the animated teacher better than the subdued teaching? Well, possibly, but we have different weather in fall and versus spring. Fall ends gloomy, spring ends pleasant. Possibly. People are usually, at least this is the way I was, and I think most people are probably like this. In the fall, after your summer break, you're kind of a little bit more ready to get back into school. In the spring, you've kind of, you went through the grind of the fall, you had a little break for Christmas, and then you come back in the spring and you're not quite as fresh coming off that long summer break. And maybe in the spring, like it says, pleasant weather, you're a little bit less motivated to stay in a classroom. You'd rather be out doing stuff. So weather could be it. There could be other things too. So, but it suggests weather here could be part of this cause for the difference. And so that is what's called a confounding factor. So two factors are confounded if the levels of one are associated with the levels of the other. So in this case, it's possible that weather and the teaching style were confounded because maybe the weather is the one that's influencing the learning scale. Avoiding confounding factors can introduce new ones, comparing morning and afternoon classes. So again, that could be a similar thing because maybe more people are not as motivated in the mornings versus afternoons, or vice versa. That's definitely a personality issue there, but that could be another confounding factor. And then we talked about lurking variables in the chapter on scatter plots. So lurking variables create an association between two variables that tempt us to think one may cause the other. So these are pretty similar ideas, and they can be a little bit confusing. So confounding factors, this is where you're looking at two things that could be causing the response to move. So the response being the y variable. Confounding factors, we have two different things that could be influencing the response, whereas a lurking variable is a third variable that is causing both of the other two to move together. So I think we mentioned age and wrinkles and gray hair in the chapter on scatter plots. So that'd be a lurking variable because the age is the lurking variable that's causing more wrinkles and more gray hair. Whereas the confounding factor, we have the weather and the style could be both affecting the response, which would be the amount of learning. So they're very similar, and it does take a little bit, seeing a few examples and maybe Google some examples, other examples. What's an example of confounding factors versus lurking variables, because they're slightly different. They are a little bit, I don't know if they're related. I guess they probably are related a little bit, but they are different. And so you want to make sure that you have that difference in straight in your brain. Okay, so if you have any questions, feel free to email me and we'll get those answered, or post in the discussion boards also. You can do that. So